to J by C d omega by dt plus IL. Correct?
Yes, sir.
Start recording. Yes. Okay, so this equation has come from here. IA is equal to J by C d omega by dt plus 1 by C into TL. And TL is equal to C into IA. Okay? Or current will be equal to TL by C. So this TL by C is your load current IL. Okay? IL is equal to TL by C, that is the load current. Or from equation 4, which one is equation 4? From this equation, omega is equal to omega L plus omega in minus omega L e to the power minus T by EEM. We can write that, if we differentiate this equation, what do you get? The
Minus C by T.
left hand side is d omega by dt. That is equal to
Minus C by T.
this load speed is constant. Its derivative will be 0. This omega in minus omega L is also constant. So it becomes minus C
by TEM. By TEM into e to the power minus T by T.
Correct. Okay. Substituting this, if we substitute this in the equation that is written above, we get IA is equal to J by C multiplied by d omega by dt is minus C upon TEM e to the power minus T upon TEM plus IL. Okay. Or it is equal to these two constants are different. These two constants are different, otherwise they will get cancelled. Okay. So this is your equation for armature current. IA is equal to minus J by C multiplied by C1 upon TEM e to the power minus T upon TEM plus the load current IL. Now there is a constant here, a new constant, that is C1. And this C1 can be found out by using the initial condition. What is the initial condition? The initial condition is that at time equal to 0, IA is equal to the initial current IN. Correct? At t is equal to 0, your armature current is equal to the initial current IN. So if we substitute t is equal to 0, this becomes 0. E to the power 0 is 1. Okay? And your IA becomes equal to IN. That gives you C1 is equal to minus C TEM upon J multiplied by IN minus IL. Correct?
Yes, sir.
If you substitute this in the above equation of IA, so IA becomes equal to minus J upon C TEM multiplied by C1. C1 is minus C TEM upon J into IN minus IL multiplied by e to the power minus T upon TEM plus IL. Okay. So this CC, TEM, TEM, JJ, everything gets cancelled, and you are left with minus minus plus I in minus IL multiplied by e to the power minus t upon TEM plus IL. Okay, this is the equation for IA. ठीक है, the armature current is equal to I in minus IL e to the power minus t upon TEM plus IL. Okay.
Yes, sir.
Yes, sir.
Now the initial current, the general equation for the initial current I in is equal to V minus E upon R. In general, the initial current I in will be equal to V minus E upon R. Now when the motor starts from rest, suppose we are starting the motor from rest at t is equal to 0, then the value of E will be equal to 0. So your I in becomes equal to V by R. That we also call as the short circuit current ISC. Correct? And so in that case, your IA becomes equal to short circuit current minus IL e to the power minus t upon TEM plus your load current IL. Okay. Also, if your motor is starting at no load, then IA is simply equal to ISC e to the power minus t upon TEM. Okay.
Okay, sir.
So, based on these two equations, we can plot the armature current as the function of time. Let us say this is your short circuit current ISC. Okay, that is equal to V by R. And this is the value of your load current IL. So, when your motor is starting at no load, this equation is applicable. So, when time is equal to 0, your IA is equal to ISC, and then your armature current will be simply an exponentially decreasing function. Correct? When your motor is starting at no load, initially, the initial current is equal to the short circuit current V by R, and as your motor keeps on gaining speed, your armature current goes on decreasing exponentially with respect to time. And finally, it becomes 0 when time becomes infinite. Okay? Clear? If you draw a tangent to this curve, then this is your time constant, TEM. Okay? And what about when the motor is started at load? Okay? Then initial current e to the power 0 is 1, so it becomes ISC minus IL plus IL, that is still ISC. So your initial current is still equal to ISC, but your final current is now equal to IL. Correct? Yes or no?
Yes, sir.
Final current.
Yes, sir.
Yes, sir.
Steady state, this term becomes 0, so your final armature current is equal to the load. Okay, so these are your armature current curves as a function of time during starting, with load and without load. Okay. Now it is common practice. It is common practice to have your starting rheostat in steps instead of keeping the rheostatic external rheostat constant during the whole period of starting. It is common practice to have steps of rheostats, and as we have seen earlier, and if you remember, we have also designed the external resistances. Yes or no?
Yes, sir. Yes, sir.
Yes, sir.
We had also determined what should be the value of external resistances to start the motor. Okay. And if you remember, in that case, we had taken two current limits, I1 and I2. And the starting current was restricted between those two limits. Whenever the current exceeded, it is I1 is the upper limit and I2 is the lower limit. I1 upper limit, I2 lower limit, or
It's I1 lower limit, I2
I1 upper limit,
maximum
sir.
value, and
I2 and lower limit.
I1 was the upper
and
limit,
20%.
I2. Let us say I1 is the upper limit and I2 is the lower limit. So whenever the current exceeded I1, a step of resistance was cut out, so that the current decreased to I2. Correct? If you are taking I1, let us say I1 is the upper limit and I2 is the lower limit. So whenever the armature current exceeds beyond I1, initially armature current will be I1. Okay? As the motor speeds, it will decrease and it will reach the value I2. As soon as the current reaches I2, we cut out a resistance so that the current once again jumps to I1. Okay? Again, it decreases because the value of E is increasing, and whenever it reaches I2, we again cut off a resistance. Correct?
Yes, sir.
So in that case, how will be the graph of armature current during starting? So let us say this is your lower limit of current, that is I2, and this is your upper limit of current, that is I1. So you are selecting the external rheostat such that at the instant the switch is turned on, your short circuit current ISC, that is equal to V by R, must be equal to I1. Correct?
Yes,
Priya?
sir.
Priya,
What, sir?
I'm asking Priya, is this correct, Priya?
Yes, sir. Yes, sir.
At the instant of starting, you are selecting the value of external resistance such that your short circuit current ISC, that is equal to V by R, must be equal to I1.
Yes, sir. Yes, sir. Yes, sir.
Because I1 is your upper limit of current. Now, as the motor starts, its speed increases, its back EMF increases. So your armature current will go on decreasing. How it will decrease? We have just seen that it will decrease exponentially. Correct?
Yes, sir.
Yes, sir.
At this instant, the current reaches, the current falls to I2. Now, to have faster starting, we don't want the current to fall below I2. So we cut off a section of resistance. And the section of resistance is so designed that as soon as you cut off that section of resistance, your current jumps back to I1. Provided, of course, that you are neglecting the armature inductance. Okay? If you consider the armature inductance, it will take some time to reach I1. Okay? So let us say this time is Tx1. Now once again the motor speed increases. So again your current falls exponentially. And again it reaches I2. And let us say this time is Tx2. The question is, are Tx1 and Tx2 equal?
Sir, I'm just asking, sir, first one thing,
No,
sir.
sir.
Sir, sir, in the in the sir induction of the motor, when we have connected the external resistance in the induction of the motor, so starting current reduces, and the full load current of the motor means starting current means we try to reduce the starting current, but I'm just asking means the full load current and the starting current will always be more than the full load current. How much we try to reduce it, but it will be more than the full load current of the motor.
Yes.
So how much we can reduce means by which extent we can reduce our starting current to full
We
load
can
current.
we can reduce the starting current to full load current. We can even reduce the starting current to a value less than the full load current. It is in our hands because we are connecting an external resistance to limit the starting current. है ना?
To value
But
less than the full load current of the motor.
yes, you can decrease it to any value that you want.
It
The
will give the
question is,
starting torque. It will give the starting torque very high, but I'm just asking that starting torque will be high, but it will not means it will not give any other problem to our motor. Means we try to reduce the current means below the our full load current.
where
Will
are we? We are in the DC motor or the induction motor,
I'm in the induction motor. I'm in the induction motor.
but the class is going on DC motor. So
So I'm just
I'll
asking. I'm
explain.
just asking.
Uh,
I'm just asking.
hmm.
Means if it will not harm to our motor means we are giving the high torque starting torque high starting torque to our motor, so means
ठीक है. Now let me answer. ठीक है? And I'll answer in the context of the DC motor. The DC motor, you can have any value of starting current. है ना? This current I1 that you see, how much is that current I1? That is entirely up to you. That I1 can be equal to the load current also. It can be less than the load current also. Okay? So you have to decide. And you will decide that I1 should be greater than the load current. Both I1 and I2. Why? Because it will give you faster value of, short starting time. The more the current, the more the torque, the faster your motor will start. Correct? And how fast, that depends on how much current your motor can handle. Okay, so that upper limit is decided by that. So similarly, in the case of your induction motor, it is up to you. Okay, how much torque you want to give, that your motor must be able to handle that much torque, current, all those things.
so in the external high resistance means high
Hmm.
external resistance we are adding, so all these means will matter. uh, we
You are
want to
you are
reduce the starting
adding.
current below the full load current of the motor is
I don't think
Yes.
you'll ever have starting current below the full load current. Okay.
is
If you have that, I don't think your motor will start. Okay. I'll think about it, tell you later. Okay, but you will never have your starting current. Okay, too much resistance will be required. Starting efficiency will be poor. Starting time will be increased. Lot of things. There is no such thing as black and white. Okay, if you improve one thing, the other thing regresses. If you improve the other thing, the first thing regresses. So it is all about compromise. Okay, choosing the optimum point, optimal values. Okay. Sure. Okay. So the question that I was asking was, is Tx1 equal to Tx2?
So not equal to, sir,
Not equal to, sir.
because in case of first starting, if T1 and T1 and T1 and T2 will be equal. If
This
not,
Tx1,
resistance will not equal to
this
Q1 next to
Tx1 will
N1.
depend on the time constant, and because the time constant in the first case is greater than the time constant in the second case, Tx1 will be greater than Tx2. Okay.
So, yes, sir, what you are showing here by this means by this curve, what you are showing means here you have shown means 2 e to power minus x curve means whatever tx1 and tx2 for tx1 and tx2 means what you are saying means these are two starting means two starting of our
It's not two starting. You are reducing the external resistance in steps, starting resistance.
means when we have we have changed the value of resistance at that instant our current will goes high.
Yes,
Okay, at that means when at the time of changeover of resistance external resistance. Okay, okay.
okay. So at this instant, once again, your current reaches the lower limit I2. So you again cut off a section of resistance so that your current jumps back to I1. Again, it decreases exponentially to I2. As you can see, the time constant or the time required has again decreased. Okay. Suppose you are using only 3 sections of resistances. At this instant, you again cut off the third and last section of the external resistance. So again, it jumps back to I1 and then it will fall. Till where it will fall?
Load current, sir.
Yes. Then it will fall to the load current IL. And it will remain constant there if we are assuming that the load is constant. Okay? Clear?
Yes, sir. Yes, sir.
Yes, sir.
Can we find the value of Tx1? Can we find the value of Tx1?
So it will be a time constant for the
No,
first.
it is not the time constant. It is not the time constant. It will be the time constant if some 63.3% comes. And if I2
Sir.
is between I1 minus IL, 63.3% of I1 minus IL, if you have I2 somewhere, then it will be the time constant. But that is not the case. Okay. So how can you find Tx1? We can find Tx1 by using this equation. IA is equal to this one. Right?
Yes, sir.
Yes, sir. Yes, sir.
So IA for this case,
This IA will be I2 and IN will be I1.
yes, it will be I1 minus IL e to the power minus Tx upon TEMX plus IL. Okay, I have not put 1 or 2 there because it is applicable for 1 as well as 2 as well as 3. Right?
Yes, sir.
Of course, there is an X there. Okay? And it will change with the section. The time constant will change. Okay? So you can find Tx1 by putting TEMX1, Tx2 by putting TEMX2, and Tx3 by putting in TEMX3. Okay, so it is very easy to solve this equation. It will simply be this will be I2 minus IL. I'm still with the pen or not? Yes. So this IL goes there. It becomes I2 minus IL divided by I1 minus IL. And then you take the natural log that will give you Tx is equal to TEMX multiplied by natural log of I1 minus IL divided by I2 minus IL. Correct? Yes?
Yes, sir.
Yes, sir.
Yes, sir. Yes.
Yes. You notice something about this equation? About this term? You
So it
notice
is
something?
constant for IL
Yes.
constant.
Also, if load current will be
If the load current is constant,
No.
that means your Tx is equal to some constant C2 multiplied by TEMX. Okay? So these times are directly proportional to your time constants. As your time constant decreases, these times also go on decreasing. Okay?
okay, sir.
Yes, sir.
ठीक है